started.
Okay, so the last couple classes we've talked about the calipers, micrometers, and other gauges. Should note there is a quiz out there on that. That is due. No. By noon tomorrow. That October 2nd. I left some space up above it because there's a couple of quizzes up there that I mentioned earlier, but I haven't been reminding you of. I just want to make sure. There's a quiz 10 for both that was technically due yesterday, and a quiz 10 for apps that is due at noon today. I forgot to mention those again yesterday. I should have. So I'll be a little lenient on those. As long as you can get them to me by Monday, I'll be okay. Those are both a little bit tougher quizzes, especially the 10 for apps. That's the one that's got the stainless steel countertop and surface areas and stuff like that. Those are a little tricky. But just be aware that those are out there. If you haven't completed them yet, get them into me as soon as you can. Okay, well, today we're going to pull back from the measuring devices, and we're going to go back into our calculated measurements again. We're going to talk about volume. So volume is originated very much like our length and our area. There's a quick review. Remember, we started with a point, and we moved that point in a single direction, and that distance moved was a length. That created our line segment. And then we took that line segment, we moved it in a second direction. Oops, not what I wanted. And that created an area. And the size of that area, of course, was related to that original length times the distance that we moved that line segment, which we said was usually referred to as a width. And all of our areas, as we've said, refer back to this rectangular shape. Triangles, trapezoids, even circles, we turned them into rectangles so that we could come up with a way of formulating their areas. So let's take that rectangle, and let's say it's sitting on the ground, and picture it as though you're up above, kind of looking down at it at an angle, so it looks kind of skewed like that. And now, just like we moved the line segment to create the rectangle, here I'm going to grab onto that rectangle and I'm going to stretch it up in through space. It's going to create a box. When we do that, the original shape that we started with, this rectangle here, use the mouse for that, I guess. They could slide, we grabbed that rectangle and we pulled it up through space to create the box. That is called a base. The volume of any object is found by calculating, I'm going to actually move it down here, the area of a base, and once again times the distance that that base has been moved, and we call that a height. Now, to define that height, what is the height? We think of height as being up and down, and in this case, that's in this exact example, that's true, but it's not always true with volume. We had the base on bottom here. That's where we started with it. We pulled it through to create the object. It ended up on top here. The height is the distance that base moved from where it started to where it stopped. That is our height. Now, realistically, when we look at a box, it's really impossible to tell which side is the base, because technically any side of that box could be the base. I could take the bottom and pull it up through, I could take the end and pull it across, or I can take the back and pull it out. Any side of that box could be the base. So it is traditional base, you think of bottom or lower portion. It's traditional to take the bottom of that box as our base. But it won't always be the bottom in our other shapes. We'll look at other shapes here in just a minute where it's not the bottom as the base. Well, let's say this is 12 feet by 7 feet by 8 feet. So to find the volume here, we'll find that A with the little b refers to the area of the base. The area of the base here is just a rectangle. We're going to use the bottom again, 12 feet by 7 feet. Or 84 feet squared, or square feet. So then the volume is just the area of that base, the 84 square feet, times the height, which is going to be the 8 feet. I believe that is 672 square feet times feet is feet cubed, or cubic feet. So that is a box where, like I said, we could have picked any side of that box to be the base. But there are a lot of shapes out there where we don't have that freedom, that we are limited to what we can use as a base. For this shape here, this has to be our base. That's the shape that I pulled through to create that object. A three-dimensional object is referred to as a solid, by the way. So you would say that that is the, that is the shape that we use to create that solid. So the base, like I said, is that blue portion. So the area of the base is that triangle. It's 12 inches by 5 inches, and of course divided by 2 because it is a triangle for 30 square inches. So then volume, once again, is just the area of that base, that 30 square inches, times the height. Now the height, again, remember, is the distance from where the base started to where it stopped. So this is the height, that 20 inches. 30 times 20 is 600. Inches squared times inches is inches cubed. So 600 cubic inches is our volume. Let's look at our cylinders. Here it's pretty obvious that the base is the circle, and that circle has been pulled up through to create that cylinder. So obviously the circle is our base. Let's look at a diameter here of 10 millimeters and a height 16 millimeters. So once again, we need the area of a base. So the area of the base here, the base is a circle, so it's going to be the area of a circle. Pi times 5 squared. Diameter of 8 millimeters, so the radius would be 5 millimeters. Giving us the area of that base is 78.5 millimeters squared. So our volume is simply the area of that base, 78.5 square millimeters, times that height of 16 millimeters. 78.5 times 16 is 1,256 millimeters cubed is our volume. This method of calculating volume, a lot of people are like, well, what about just length times width times height? Well, yeah, that works for a box, but the reason I define it the way I do is the area of a base times a height is, as you can see with all these other shapes, the triangular solid here, the triangular prism, or the cylinder, it becomes the same formula. You find the area of that base shape and multiply that area times the height to get a volume. And by doing it this way, it allows us, we can actually use some very irregular shapes. Like this. Oh, come on now. There we go. So this is obviously the base here is a rectangle. So we're going to go as 12 inches by 8 inches. We'll give it a height here of 10 inches. We can find the volume of this just fine. We'll cut the base across here and we'll divide it into two shapes. So to find the area of our base, we've got shape 1, which is a 12-inch by 8-inch rectangle, or 96 square inches. Shape 2 is that half a circle, which will be pi times, it's 8 inches across, so we're going to use a radius of 4 inches squared, and of course divided by 2 because it's only half a circle. Which gives us 12.56 square inches. Giving us the area of our base. Actually, that's not 12.56, is it? Let's actually calculate that out. 25.12, I believe, but I'm going to double check myself. It's been one of those mornings with the internal calculator here. It is 25.12. So that gives us the area of a base of 121.12 square inches. So then the volume is the area of that base, 121.12 square inches, times that height, the 10 inches. So 1,211.2 inches cubed is our volume. So as you can see, this allows us to find some really strange shapes if we wish. As long as we can find the area of its base, if we can break it down into pieces we can find the area of, and then, as long as it's consistent, it's what we call a prism. So that means that the base on one end and the base on the other end are identical. And a little bit of vocabulary, the surface that connects those bases, part that wraps around here, that is what is called a lateral surface. And when we start talking about surface areas, that term lateral surface will come into play. But all the lateral surfaces is it's the surface that connects the bases together in that solid object. Let's talk about a volume application here. A big volume application is density. To define density, we've defined volume, but we also need to define mass. Mass is the amount of matter in an object. Now, a lot of people confuse mass and weight. They are very tightly related. The more mass an object has, the more it's going to weigh. But weight is measuring the force of gravity on the object. So weight depends on gravity. Mass does not. Mass is literally the amount of particles, the amount of material within that object. Now, with that said, on Earth, you can calculate the mass of an object by finding its weight first if you want to. Density describes how tightly packed that mass is. So it is the amount of mass in the object divided by the volume through which that mass is spread out. The larger the volume is, the lower the density is, because those particles can be more spread out in a larger space. So let's say I have an object that has a mass of 27 kilograms and a volume of, let's say, 900 centimeters cubed. Or 9,000, I should say, centimeters cubed. You might think that sounds like a lot, but 20 centimeters is less than the width of our computer screen here. 20 centimeters really comes down to, what is it, about 10 less than 10 inches, is about 8 or 9 inches. Actually, it's almost exactly 8 inches, excuse me. 20 centimeters by 20 centimeters by 20 centimeters, 20 by 20, gives us the area of a base of 400 centimeters squared, and a volume times another 20 would be 8,000 centimeters cubed. So that 9,000 centimeters cubed is really just a little bit bigger than 8 inches by 8 inches by 8 inches. 27 kilograms is about 60 pounds. So that's quite a bit of mass. So the density we would get there would be our 27 kilograms over our 9,000 centimeters cubed. 27 divided by 9,000 is 0.003. That'll be kilograms per centimeter cubed. We can keep our units. We just combine our units for that rate. Just like with any other operation, when we multiply or divide, we combine the names. Kilograms divided by centimeters cubed gives us kilograms per centimeter cubed. Now you look at that, that looks pretty small, but remember, a centimeter cubed is pretty small. It's about the size of a sugar cube. 0.003 kilograms in that size is actually relatively dense. So let's say we have something with a density of 600 grams per centimeter cubed. Sorry, 60 grams, not 600. 60 grams per centimeter cubed. And it has a volume of, what do I want to put in here? This really doesn't matter. Go 800 cubic centimeters. I can find the mass by rearranging that formula. Density equals mass over volume. I can rearrange that to get an alternative of mass equals density times volume. So I can use this information to find the mass of that object. The density of 60 grams per centimeter cubed times 800 centimeters cubed. So we have grams per centimeter cubed times centimeters cubed. That cancels out the centimeters cubed. Think of it this way. 60 grams over 1 centimeter cubed times 800 centimeters cubed over 1. Centimeters cubed cancels out. 60 times 800 is 48,000 grams. Which, when we look at our units of mass, we'll know that we can convert that to just 48 kilograms. Now, there's a reason why I'm using metric units here. Density in standard units is actually kind of tricky. In the standard measuring system, we tend to focus on weight rather than mass. The units that we're used to, pounds, ounces, and all that, those are actually units of weight, not mass. And we'll talk about it in a little bit more when we hit the mass units. But the slug is actually the unit of density in the standard system. Now, we see things all the time that are listed as pounds per cubic inch or pounds per cubic foot. Like a lot of your woods, they go between 38 and 65 pounds per cubic foot. Well, that is technically not a density. A density would have to be in slugs per cubic foot. But I'm willing to bet that outside of a science class, none of you have probably ever really used a slug for anything. It's just one of those units that has kind of worked its way out of use. In engineering and science is really about the only place the slug still pops up its little head. We talked last week about converting areas. Things like 4 square feet going into square inches. And how we had to adjust our conversion factors. Square feet into square inches is not going to be 12 as our conversion factor. 1 square foot is actually 144 square inches. That 144 is actually 12 squared. So the square feet cancel out. 4 times 144 is 576 square inches. On bottom, it's 1 times 1, so it's just 1. So that's 576 square inches. Well, what if this was for cubic feet? Going into cubic inches. Well, a cubic foot is 1 foot by 1 foot by 1 foot. But we know a foot is 12 inches. So that cubic foot is 12 inches by 12 inches by 12 inches. 12 by 12, excuse me, 12 by 12 by 12 is 1,728 cubic inches. So 1 cubic foot is 1,728 cubic inches. So we take our 4 cubic feet, put it over 1, put cubic feet on bottom so they cancel out. 1 cubic foot is 1,728 cubic inches. So the cubic feet cancel out. We've got the 4 times the 1,728, which is 6,912 cubic inches. So 4 cubic feet doesn't sound like much. 6,912 cubic inches sounds like a lot. But again, it's because our units are going in 3 directions. Those conversion factors get large very quickly. One that I've used a lot in my life because I've poured a lot of concrete is this one. "567 cubic feet going into cubic yards." When you hear concrete being ordered, you hear it's ordered by the yard. Well, technically, it's actually a cubic yard that they're ordering. So just like with our cubic feet, cubic yard is 1 yard by 1 yard by 1 yard, which a yard is 3 feet. So that's 3 feet by 3 feet by 3 feet. Well, 3 feet by 3 feet by 3 feet is 27 cubic feet. So 1 cubic yard is 27 cubic feet. So we put cubic feet on bottom, cubic yards on top. The yard's the bigger one, so it's 1 yard equals 27 cubic feet. Cubic feet cancel out. We got 567 cubic yards on top over the 27. We divide that out. I believe that's 21 cubic yards. So we have to be very careful, depending on whether our units are feet, square feet, or cubic feet, the conversion factors change. When we go to the metric system, to recall, if we were converting $46,000 centimeters into meters, from centimeters to meters, there's 2 spots to the left on the chart. So we just took our decimal point, which is at the end of the number, and moved it 2 spots to the left. That's 460 meters. But if it were 46,000 centimeters squared, going into meters squared, now we had to change it up. Now every spot on the chart is 10 squared, or 100, which is 2 decimal places. So it's 2 spots on the chart, but that means it goes 4 decimal places to move. So 1, 2, 3, 4, that's 4.6 meters squared. Well, let's go one step further. 46,000 centimeters cubed, going to meters cubed. Well, now every spot on that chart is 10 by 10 by 10, or 1,000, which means it's 3 decimal places. So 2 spots on the chart is 6 decimal places. So we go 1, 2, 3, 4, 5. We have to add a 0 to go 6. That's 0.046 meters cubed. So if I have 2.8 centimeters cubed going into millimeters cubed, from centimeters to millimeters is 1 spot to the right, but this is cubed, so that spot is 3 decimal places. So I go 1, 2, 3. You have to add zeros. That's 2,800 millimeters cubed. It's 7.1. I used the wrong abbreviation. I should add another M there. If it's 7.1 centimeters squared going into millimeters squared, it's still 1 spot on the chart, but it's only squared. So since it's only squared, it's only 2 decimal places per spot. So I go 1, 2, add a 0. That's 710 millimeters squared. So the moral of the story is we have to be very, very careful with these units. Make sure if you see the squared on there, make sure you know you have to adjust your conversion factor. Or if you see the cubed on there, you're going to have to adjust the conversion factor for that. So for homework, in the little book, it is unit 31. Of course, the odds. In the big book, we have page 702, exercise 28-1. Page 706, exercise 28-2. 709, exercise 28-3. That's the area, the volume calculations. Then we're going to have page 299, exercise 8-7, and page 300, exercise 8-8. Those are the conversions of those units. Also remember, you have quizzes. You have the 10-4 both quiz. You have the 10-4 apps quiz. And of course you have the caliper and micrometer quiz. I think that's plenty to work on for today. So we'll end it there. If you want to stick around and work, I'll